A very good morning to all. On behalf of the organizing committee of IBWGST 2021, I welcome you all to the 11th lecture of this workshop. As this workshop is progressing, it's getting more and more interesting with many speakers, renowned speakers across the globe. Today we have with us Professor Sebastiano Di Amico, a renowned geophysicist from University of Malta, who will deliver his talk on seismotectonics of Central Mediterranean area. Before we proceed, may I request our session chairman, Professor J.R. Kyle, sir, former Deputy Director, the Director General of Geological Survey of India, for his initial remarks. Over to you, sir.
Thank you so much. I think it's our great pleasure and honor to have Professor Sebastian with us today morning. And we are already collaborating with him in many aspects. And we had a nice time together in Jorhat. So warmly welcome you, Professor Sebastian. Thank you so much for kindly accepting our humble request. And we all look forward to listening to you, your very excellent lecture on this topic. So we look forward. Thank you so much for accepting. Thank you.
Thank you, sir. So now I'm going to introduce our today's speaker, Professor Sebastiano Di Amico. I'm going to read out his brief biodata. Professor Sebastiano Di Amico is serving as a senior lecturer at University of Malta since 2014, before which he served as the university as research officer from 2010 to 2014. He also has a very rich experience of serving as a visiting research scientist, adjacent faculty, research fellow researcher at several universities from Italy and US. Professor Di Amico completed his PhD in geophysics from University of Naples, Federico II, Italy in 2009. Prior to that, he pursued postgraduate course on practical vacuum and cryogenics in 2005 and master degree from University of Messina, Italy in 2004. His scientific interests include the characterization of rupture processes from complex, recent, and historic earthquakes, volcanodynamics, moment tensor solution, waveform modeling, and inversion, analysis of ground motion hazards and site effects, earthquake source physics, microseismic intensity earthquakes scenario development, etc. A few of his notable professional experiences includes Vice President of European Seismological Commission, Executive Committee member of European Seismological Commission, Coordinator Geophysics Laboratory, Coordinator of Association of Italian University Professors and Researchers in Malta. He has published more than 350 research papers and has served as an editor of more than 10 reputed journals. As I can go few more minutes, but due to time limitation, I will conclude here and request Professor Di Amico to take the digital space and enlighten with his lecture. Thank you, sir. Over to Professor Di Amico.
Thank you, Chinmay, and good morning, everyone. I will just start my camera off now, so just to save bandwidth, and maybe it will be a little bit more stable. Can you still hear me?
No, sir.
Can you hear me?
Yes,
we can hear you, sir. But
Okay,
your presentation is not yet loaded.
No, I'm trying to share my screen. Just one sec.
Okay.
Now should be able to see my screen.
You can put in selection. Yes, selection.
Do you see it?
Yes, sir.
Yes.
Okay.
Yes, perfect.
Good morning again, everyone. Thanks for the invite and for having me here. It's really a pleasure and an honor to deliver this talk this morning. Today we're gonna talk and see some part of activities and scientific approach related to the seismotectonics and in general the geodynamic of the Mediterranean area. And we will have a little bit of focusing within the central Mediterranean because even though it's not a large area and even if it's controlled by the main tectonic regime that we're going to see in a few minutes, still it's a quite complicated area because once you start looking into it, you see some differences coming in place. So just as we start, we'll see where we are. We are located and we're going to look at the Mediterranean area that you can see in here, like the topography and the bathymetry of the area. And even looking at these simple features, so these observational features that we can have, we can start understanding and see some particular features that are of interest and can give some hints on the fact that the area is controlled by major forces and it's could be considered quite complicated for from a geodynamic and seismotectonic point of view. And this also pose a kind of a hazard in respect to this phenomenon. So we're gonna see some of these aspects. I think it's fair to start with the evolution of the Med. And in this picture, we do have several steps starting from 35 million years ago up to the present situation. Let's see if I can get the pointer. Can you see the pointer? I hope so. So we
Yes,
are.
sir, we can.
Thank you. So we're starting from the 35 million years ago down to the present situation. As we can see, we don't have an active subduction zone, so it was quite active in the past, and now, as you can see from the present situation, is active in very little areas if we compare with the subduction margin that we had, for example, 35 million years ago. Of course, this gives rise also at volcanic activities, and we do have a certain number of volcanic activities that are usually associated with the subduction phenomenon. And the subduction phenomenon, because even of the rolling back of the slab and local geodynamic forces, will create also an extension area of where we do have the presence of a lot of normal faulting, and we will see in a bit. Of course, we don't have, and we can consider even the evolution looking at the directions of all the arrows that we don't have on this diagram to have a clue on the stretching directions that we have in this particular regard. This is another view in which we also have an indication of the velocity. So as you can see, the velocity has been estimated in very few centimeters per year. And we start here from the middle Miocene down to the present situation. And as you can see, the evolution of the central Mediterranean has been not as steady as we might think. Obviously, all this has a general introduction will have repercussion on the probabilistic seismic hazard assessment, because knowledge of the geodynamic, knowledge of the present situation will also be considered a very important point in the estimate on the probabilistic seismic hazard analysis. So as you can see, this is the probabilistic seismic hazard analysis for the entire Europe, and we see that there are places with high probability of exceedance in the next 50 years located in the central Mediterranean part, so Italy, Greece, and Turkey, okay, above all. So everything is controlled by the ongoing processes, and we'll try to see what are these processes and how we can have a clue on these processes to picture the situation and the seismotectonic situation that we have at this moment. If we look at this from a seismicity and active faults point of view, and we look at the entire Mediterranean basin, so from west to east, we stay like from Portugal, Spain, the Iberic Peninsula, down to the Anatolia region, we do see that is really, really full of active faults, okay? And the shape and the orientation of these faults will start giving us a clue on what's going on. Another important features that will help us in understanding the situation over here and what is the what's going on in this part of the world is having a look at the seismicity. The seismicity is depicted in the lower panel here, and as you can see, most of the seismicity is within the 30 kilometers. This is the crustal seismicity, but it's very clear that we don't have even deepest seismicity, and we don't have in particular deepest seismicity in this part, so the southern Italy, where we will see that there is like still subduction going on, and we mentioned it already. And in this particular area, we don't have seismicity that can reach down to 500, 600 kilometers on this slab that is dipping in this direction. And same into the Hellenic arc, as you can see even from here, from the orientation of the fault, there's still subduction taking place, and we don't have a lot of earthquakes, even deep earthquakes within the 300 kilometers. So even if we don't have two subduction phenomena which are separated apart few hundred of kilometers, they are controlled by the same kind of a mechanism, but the two slabs, they have different features indeed. And in particular, the Calabrian arch underneath southern Italy is a little bit deeper and steeper than the Hellenic arc one. So if we have a look now on a polished, let's say, map in which we don't have the main seismogenic areas, we can see that we don't have several margins. We don't have, again, a clearer picture now, instead of looking just at earthquakes, but at this kind of view on the bathymetry. And we can see even the depth and the increasing depth of these subduction plates over here and over here in this direction, and the different tectonic regime that we will then look into more details in a little while. So we do see a margins with a lot of thrust fault, okay, And a lot of normal faults are also present into this system. In Italy, the upper part and within the first 30 kilometers is everything controlled mainly by normal fault, and we do see the subduction contours, so we can appreciate how steep and narrow eventually this it's gonna be, so into the Calabrian arch, and how it's a little bit larger, the subduction area under the Greece, the Hellenic arc and the Cyprus arc, and how those two slabs are a little bit different. So we're talking about a small place in which we don't have earthquake phenomenon. Some of them can be quite energetic, and most of them, the contacts are in the sea. So this gives rise also to potential tsunamis. And in here we do have a kind of simple picture in which we do have a representation of the potential tsunamigenic places here, dividing between among low and very high. Okay, so the Mediterranean area is quite active, is also from a seismogenic point of view quite active, and with a lot of events that can reach magnitude 7 and above, so quite strong. So they can cause damage, but also they are potentially generating tsunamis if the conditions are right. And as you can see from this point of view, when we speak especially about tsunami and we look at the early warning system, just as a note, the situation in the Mediterranean area is quite different than the one that we can have in the Indian Ocean, Pacific Ocean, just because of the spaces, right? So from here to here, so from Sicily to Greece and vice versa, in about half an hour, the tsunami wave generated on one side will hit the other side. So, and the recent earthquake that happened over here also showed that they generated a tsunami, and also showed that there's a lot to do in order to increase the detection capacities and the capabilities, because in some particular cases, at very close distances, we are in a kind of a shadow zone from this point of view. So if we now try to combine, even in this exercise, everything together, we'll see the main plate tectonic setting of the Mediterranean in this picture, in which we do see the collisional front, so everything is controlled by the pushing of the Africa against the Eurasian plate. We do see the subduction over here and underneath the Hellenic arc and the Cyprus arc, and we do actually start picturing the complication of this particular area from this geodynamic and seismotectonic setting point of view. Obviously, since we're talking about the tectonic setting in here, and we're talking about plates and the main African plates moving against the Eurasian plate, we can see from here the some numbers now in terms of, and they are on terms of up to few centimeters, couple of centimeters per year, while on the right hand side we see the vertical rates. that will go in the order of 2 or 3, up to 2-3 millimeters per year. Okay. If now, with the eye of a seismologist, we look at the same features, looking at the moment tensor, and this is just a representation of the moment tensor for the largest event, we could see and we can start interpreting that the situation is a little bit more complicated than the actually we can schematize. And once we go closer into the picture, we will see that there are like some strange, let's say, colors on mechanism that are actually giving them some hints that something different is going on. So we don't have, as we said, a thrust kind of mechanism over here and normal faulting over here. Same for the Hellenic arc. This is the beginning of the subduction zone, and we don't have a big normal and extension regime over here, but also we don't have the presence of this strike slip or this strike slip events over here. How they come? So they can help us in actually understanding what's going on in this region. Just to have an idea also on the crust, those are like several model, and we don't have the more depth in here. And as you can see, the more depth varies from 10-20 kilometers up to 50 and more kilometers in some parts. So they agree more or less. And as you can see, some parts are thinner than some others. Okay. Obviously, this creates, and it's a nice place in which people that are working closely into the geodynamic matters are having fun, and because it's a kind of a small and complicated area with lot of patches here and there, and as you can see from this cartoon, we are depicting in here a potential pattern of the mantle convection that is acting now in the Mediterranean. Okay, so there's plenty of things to do, even in terms of simulations, in terms of understanding of this phenomenon, that can help us in better picture and understanding the entire phenomenon. As promised from the beginning, we will be focusing a little bit more in the central part of the Mediterranean, in the southern part of Italy, in which the subduction zone is still in place, and we will try to see how we can see signs of the subductions and what's causing if we look at a smaller region. Because the smaller we look, the more complicated and more local features are going to showing up. So again, if we take this picture once again, and if we don't have our focus on the this part, we will see that the situation is a little bit more complicated than just saying that Africa is pushing against Eurasia and we don't have subductions in here. Okay, we will try to discover if there are like very kind of little and peculiar features that can help us in understanding and explain some phenomenon. Again, this is a similar map summarizing what we said already. If we look at this part of the Mediterranean, and in which we don't have the history through time of the subducting front from 30 million years ago up to now. Okay, and we don't have in white the stop processed, and we depict here the still ongoing process. But let's see what's going on in more close details. And on the left hand side, we do have something what happened in the last 2 million years, and actually what we do have in the in here. Why we don't have the presence of the subduction, and how we can say that the subduction is still active and going on just in this portion, and why we don't have the formation of the tear faults here, and how we can verify this. And obviously you can see that even through time there have been a certain kind of rotational regime controlling those phenomena. So one way to look at this lab is not just through the location of the earthquakes, that thanks to the increasing number of stations, increasing number of recordings, is always more and more accurate. So we can actually see that we do have a lot of earthquakes, and even the earthquakes that are at sea over here quite well constrained by the network. Also, they show a large depth. We said about up to 500, 600 kilometers. But obviously we can make use of classical tomography in order, in this case P-wave tomography, in order to try to understand if what happens into this lab. So on the right hand side, we do have this is taken from a paper by Neri et al. In which the authors actually perform this tomography and are presenting several depth slices at different depths, starting from 65 to 260 kilometers. So as you can see, some variation and some portions are still visible at 260 kilometers. And that's the part in which we're going to focus on today. So if we take the same images, but instead of having slices at different depths, in this particular context, always from Neri et al., we just see through some profiles. So we move from south to the north, profile A and profile E, A prime, E prime, A prime, E prime. So we are in the northeastern part of Sicily here, and in here we are in the northern part of Calabria. Calabria is this part of southern Italy, and that's Sicily. What can we notice? That if we know, what we notice is that at the two extreme profiles, so A and E over here, we don't have a different color settings, right? Different velocities. Okay, so the high velocities are interrupted in here, while in the middle between B and D, and if we look at C just to have a central point of view through these transects, we see that it's almost continuous. So this is the actual subducting slab that is going up to 300 kilometers, at least for the resolution of the data used in this paper. But so from C to C prime here, and we do see that it's continuous just here. So this slab is detached or partially detached over here and over here, but still this slab is rolling back. Gravity is still there, is doing its job, and is pulling the slab and forcing this slab to retreat a bit. And so it's still pushing because of this subduction is going on, but on the top part is rolling back. And this gives the rise to the fact that on top we don't have, so at the in the upper part, we don't have the tear folds forming because the subduction edge is retreating, so is dragging this portion in this particular direction, but the subduction system is still going on, and we don't have the formation of normal folds and normal mechanisms over here. Okay, so through in this particular picture, then we can have an idea of what's happening. So we don't have an extension regime. So if we look at this and we are in the order or 100 to 100 kilometers in this area, we are going from a strike slip regime in the crustal part to an extension regime with a lot of normal faulting, and again and here an extension regime. This is due to the subduction and rolling back of this slab. So the situation is looking locally a little bit more complicated. That's what this geodynamic model works. But how can we depict this kind of mechanisms? But from my point of view, at least, seismicity and information on seismicity, so earthquake location, going through tomography and looking at moment tensor solution, especially for small earthquakes, it's really important. Why small earthquakes? Because small earthquakes are much more abundant, so we don't have a lot of them, and we don't need to wait for the big ones, right? Even though this area is capable of creating earthquakes larger than 7, and the last notable one happened in the 1908 on a normal fault located in the Messina Strait, so in the little portion of sea separating Sicily from Italy. And about 100,000 people were killed, and complete total destruction, over 90% of building collapsed or heavy damaged. So intensity 12 on the intensity scale. So understanding this phenomenon, trying to have an idea on the motions will also create a more solid ground for continuously updating the seismic hazard analysis. And moment tensor from this point of view are a nice and simple tool to use in order to have an idea on the main seismotectonic problems that can be found in this particular area. And in particular, as I said before, the fact that we don't have very few large events, but rather a good number of small and moderate earthquakes, and a detection capability that can help us. INGV is doing a great work in this regard in maintaining and having a nice monitoring system. We can gain and have a lot of clues from this point of view. So what I'm going to show now, it's something that you can find on a paper of mine published on physics of the Earth and planetary interiors, in which I worked closely with Professor Herman and Professor Zhu at St. Louis University in USA, and with local University of Messina, with a group led by Professor Neri, in which we use the cut and paste method to look at the solution, moment tensor solution for small earthquakes. Let's see how this system works. So we use the cut and paste, and we validate those results through another method developed always at the St. Louis University by Professor Herman, and that we call, for simplicity, the SLU MT method. So basically the idea is simple. We start for an accurate velocity model. We select the velocity model, and we don't have accurate velocity model because even of tomography and good earthquake locations and good seismology study in the area. And we use those to compute our Green's function. So we use our knowledge on velocity models and compute our Green's function. So we can create our set of synthetic seismogram, and then we associate this part of the process to actually analyzing the real data. We perform some quality control. We correct for the instrumental response. Obviously, we review the peaking because we're looking at very small earthquakes, and small earthquakes are also not detected and not picked up at all the stations. So the automatic peaking sometimes is not accurate enough. So we want to review the peaking in order to decrease the error in the final solution. We rotate the component, and applying a grid search over the magnitude, the depth, the strike, the dip, and the rake, we're able to reconstruct the moment tensor solution, then the focal mechanism, and have an accurate estimate of the moment magnitude and the depth of the event by basically doing waveform fitting of the synthetic and the observed data. Now, the difference between the two methods is that the CAP method is capable of treating separately the body waves and the surface waves, so it's giving a little bit more weight because it's cutting the seismogram in the body wave and the surface waves, and is giving a little bit more weight on the P wave, so that everything is considered into the inversion process. And this will allow us also to have some less prominent effect on the fact that the location of earthquakes can be also affected by the geometry of the network. And also, if one component is not has a perfect because of any reason, this can be discarded from the inversion process. And what you see and what we have over here is an example of one event, in this case magnitude 4, recorded at several stations, in which you can see the fit between the synthetics and the observed events. This is just a zoom in of the first two lines. So we can retrieve the strike, dip, and rake, the moment magnitude, and having an estimate of the error in respect of the model that we used. One question that we might consider, because in here we said, okay, we select our velocity model. Usually we don't have 1D velocity models. So the 1D velocity model in this complicated area not always satisfies all our needs. So is the method reliable if we don't have earthquakes in different locations in which, because of the subducting slab in here, the velocity model can change quite rapidly? Okay. So in order to test this hypothesis and to look at the stability of the final moment tensor, of the final focal mechanism as depicted in this picture, what we did is trying out different velocity models. In this particular case, we did a test using 3 different velocity models. Okay, and as you can see, overall the results that we represent in here are not too bad. They are quite stable. Okay, and the other test, because we don't have stations located mainly inland and in few islands over here, and those islands are volcanic islands that are the results of the subducting slab over here. The idea is, what happened to the solution, to the final solution, if we do have a small event which is not properly recording at all the stations? So we had chosen in this particular example one event in which we don't have recordings from all these stations. It's about a little bit more than 10 stations, and in the here we don't have our solution on the B panels, just using 4 stations, okay, located 2 on one side, 2 on another side in respect of the event, just using the faraway stations, just the 3 of them, just using station located on one side of the event, or changing a little bit the initial location. So we're forcing to have the location be moved a bit in order to have our initial estimate, and using all the stations, or using the true location and all the stations. As you can see, there are like some differences in the focal mechanism, but from the point of view that we're looking at, from this, it's still a normal fault. The main component is the normal fault, and is indicating that in here we don't have an extension regime. Okay, so this is the overall results of several small events that we have. So as you can see, just looking at this, we don't have a combination of normal and a several number of strike slip events over here. So this will come to the fact that we don't have our results, that is the interpretation based on the focal mechanism, based on the seismicity of small earthquakes, using small earthquakes, that we don't have an extension regime that is due to the rollback of the slab, and we don't have the presence of the steer fault, and therefore it has been confirmed also by the strike slip regime that we see into our moment tensor solution. Now, we mentioned that the subduction over here gets the situation a little bit complicated. If we look at these things, we do have another other papers in which we show the same approach even on the other side. So this part of the slab, as we said, tomography results are indicating that the actual portion of this slab active is this one, and this slab is detached on this side and this side, and we don't have also evidences through the seismicity. We also mentioned, though, that we don't have the presence of volcanic activities. We saw this in the initial picture when we were looking briefly and in a quite fast mode from 30 million years ago up to the present. So the subduction zone in here gives rise to the formation of the Aeolian Islands here, and we don't have the presence of Etna. So we don't have, this is the volcanic islands here, or the volcanic systems here, and the Mount Etna, the largest volcano in Europe, located in here. Okay, so that has to be with the related to the local situation. So from this point of view, Etna is located in here. before we were looking at this part and the Calabrian part that is over here. And look, Etna is located almost in the middle of Sicily, going north to south. And it's a quite large volcano, okay? So we don't have the presence of several faults and the combination of tectonic regime and earthquakes related and phenomenon related to the volcanic activity. Several faults have been mapped throughout the years, and as you can see, there are like several of them, and some of them are capable of even nice event. Okay, sorry, in here is not that clear, but this is intensity 6 and 7. Okay, so recent earthquakes with an intensity magnitude greater than 4, usually 4 and 5, and intensity 6 or 7. Recently, there was a series of earthquakes controlled by a main one on this fault, the Fiandaca fault. And that on December 2018, so not long ago, had a magnitude of almost 5, okay, that caused several damage, okay, partial collapse of buildings, damage of historical buildings. So all this stuff has to be also considered if we want to preserve our cultural heritage, okay, and the results, of course, even on counted on several people that got injured because of this earthquake. This is a close-up in which so the seismicity and the understanding of these things can help even in redefining even the seismic hazard or contributing to it. That's where we are located, and the seismic history in the last 100 more years, 150 years, that as you can see, the area is not new of 2 earthquakes of this kind with intensity 7 or 8, which we are on the higher spectrum of the moderate events in terms even of intensity and potential damage, okay, especially here in which a lot of constructions are old, are back constructed back in time, so it needs to be addressed carefully. This is just to give you an idea on what this small earthquakes can do in this part of the world because of the building stock, okay, and the large presence of monuments of hundreds of years that obviously we need to take care of. So again, this is a summary. We can do the same as we did before, and same kind of approach. And in order to get our at least approximation of equivalent velocity model, we can even use the 3D velocity model that actually are quite detailed, as you can see, by the number of stations used to monitor this giant volcano. Okay, this is just to give an overview on the seismicity patterns. So as you can see, the seismicity during the sequence, the actual sequence at the end of 2018, prior to 2018, and a couple of months after December 2018. So we do have a concentration in these 2 days of large events and concentrated in this area. This is where was happening in the fault that we were mentioning before, the Fiandaca fault. So that's the number of events and the cluster between 24 and 28 February 2019, 24 December 2018 and 28 February 2019. The majority of them actually happened and clustered here. Again, in this particular context, we did the same kind of approach that we were mentioning before. This is a magnitude 3 event in which we trying to use moment tensor to understand what's going on there. And again, we're testing against potential error locations, different stations configurations, changes and variations in the velocity model, especially because we're moving from 3D to 1D. Now we're working in fully created Green's function using directly the 3D model without the complication at the end of the day, even if we do to simplify things of moving from a 3D to the 1D. Okay, and of course, we need to compare our solution with the one that is automatically generated by INGV. This is in this particular case what we see in the left panel, and that's the other method that I was mentioning before. The comparison using the Bob Zerman's codes for this event. As you can see, our estimates are not that bad. This is an overview of all the solutions that we compute so far. And what can we see is that actually there are a little bit of differences. And if we look at the summit part events, and if we look at the lower part events, because this fault has been triggered by the fluids, most probably acting and the magma rising up into the crust. So this is a tectonic fault, and we're trying to discriminate now the different regimes, even using this kind of approach. This is the differences in terms of the focal mechanism in the different portion of the sequence as we depicted and we separated. And we saw another picture just looking at the locations, but in this particular case, we don't have the computations of the moment tensor all around. And a comparisons with the maximum compression axis of the focal mechanism, which has been calculating on the most energetic events. So they do not match the regional stress field, but they are ranged radially with respect to a probably pressurization sector, which is located in the central portion of the volcano. So now, just to keep us in the picture, we are looking at very small features, how this seismology can help in understanding the tectonic and geodynamic regime. And we are zooming in, so because we started from the entire Mediterranean area, then we focus on few hundred kilometers. Now we're going to few tens of kilometers, up to 10, 20 kilometers in space. So we are focusing in and focus in a little bit more. So in general, to conclude, and I really hope I didn't talk too much, geodynamic processes commonly uses data from several sources. So combining and inverting together geodetic GPS, INSAR data, and seismology tools like the one that we saw, earthquake location tomography, moment tensor solution, and couple this with numerical model to study the evolution of a certain region from a geodynamic point of view, and give hence also an input for the seismic hazard computations. And this overall has important implication, not just to satisfy our scientific curiosity, but also because it can have important role into the earthquake engineerings, especially in the region with potential high seismic hazard. And with this, I think I can stop. I don't know if there are questions.
Thank you, Sebastiano. Over to Sinmoy.
And I hope, because I didn't have control having this in full screen, I hope that the internet connection was stable enough.
Yes, sir. It was.
Yes.
Okay, perfect. Thank you.
Thank you, Professor Tiamico. Thank you for such an insightful presentation. Now, may I request our session chairman, Professor J.R. Kayal, sir, for his comments. Over to you, sir.
Thank you. Thank you so much. I think it was so wonderful explanation and so educative. Thank you so much, Professor. Yes, I think, yeah. Somebody is talking.
Hello, Gautam, please unmute yourself. Gautam, please unmute. Yes.
Oh, thank you. So
Yes,
it
sir.
was
Sir, you can go.
really very enlightening lecture. So much fascinating to understand the complicated seismotectonics of a complicated region. Thank you so much.
Thank you.
Professor Sebastiano. I have some small queries that, you said that you prefer, or rather you selected smaller earthquakes for fault plane solutions. Now, what was the magnitude of those small earthquakes? Means how much small were those earthquakes? Down to 3 or down to 4 or what?
No, down to 2.5, 2.5, 2.7.
Really?
Yes.
But sometimes people say that, magnitude 2.5 or so, less than 3, could be due to some small cracks, or they may not represent the fault, the seismogenic fault as such. Anyway, so I just wanted to know, but it's a very good result that you have brought out from fault plane solution of the smaller earthquakes. Then I have another comments on your presentation, that you changed the 1D velocity model and you have shown fault plane solutions did not change much, and also with the azimuth changes did not much. That is a very, very enlightening information. Thank you so much. But I have another little query. You have shown that magnitude 4.8 earthquake, it was devastating and very well studied. I might have missed you. What was the depth of that earthquake? Because 4.8 caused so much damage. What was the depth of that earthquake?
That one was a very shallow earthquake as well.
I presume that, yes.
Yes, it was very shallow, and also the building stock is old, of few hundred of years, right? So it's like a masonry building, and not always built, obviously, with seismic engineering design or modern seismic engineering designs, because of the fact they told. So the combination of the fact that was shallow and in the epicentral area was located nearby the villages, obviously this made the ground shaking quite important. And maybe also potential side effects, because we are in a volcanic area, so we do have the alternation of hard layers due to the old lava flowing, then sediments on top, maybe again in some places lava flow on top. So even from a local seismic effect, so if we go even at the very small scale, things, when looking at the damage patterns, when we look at the seismic hazard, then gets more and more complicated.
Thank you so much. So nice explanations of your, seismotectonics of the very complex region. Thank you so much again. I would suppose Professor Jha would make some comments because he is a tomography man. I think he can give more comments on that. Professor Zhao, please.
Yeah, thank you so much for a nice talk. And
Thank you.
Your results quite interesting. And I have just one question for you. In one of your early slides, cartoon slides, you show a flat slab above the 670 kilometer discontinuity, right?
6, yes.
Can you show that slide again
Yes,
for me?
yes. I'll just
It's
share my
flat.
screen. I'm sharing my screen once again, just once. Oh, I think I'm sharing it. You see it? Do you see it? Can you stop me?
Yeah.
With,
Yes.
which slides are you referring to? This one with the
It's a
seismicity?
cartoon. Yeah, cartoon slide show a flat plate in the mantle transition zone, I think.
This one?
This one, yes. This one.
Mm-hmm.
Okay, so we can see a flat slab in the mantle transition zone, I guess.
Yes.
Do you have active intraplate volcanoes above the flat slab?
The intraplate volcanoes, yes, there are actual. You're asking for intraplate volcanoes, right?
Yeah,
So,
above the flat slab.
So actually there are like some intraplate volcanic activity down here, okay? Because there's like, this is the opening of the central Mediterranean. There are like few volcanic activities over here. In here are related with the subduction, and Etna is in a kind of a between. And actually, I think I was mentioning, or maybe I didn't point it clearly, but it's considered the last episode of intraplate magmatism in the eastern Sicily. At least.
What do you think is a mechanism of the magma generation?
The mechanism? The mechanism.
Magmatism.
In here, the magmatism generation is due to the subduction. So the subducting slab is actually generating magma rising up from this side and forming this Aeolian arc set of islands.
What's the depth of the magma? The origin?
The what?
Well, we know beneath the arc volcanoes, the fluid come up about 100 kilometer depth, right? 100 kilometer.
Yeah.
The magma come up. That causes arc volcanoes. But for the intraplate volcanoes, the depth of the magma source should be quite deeper.
Yes, and to be honest, I'm not a volcanologist, but it's different, and even the type of magmatism and volcanic activity between Etna and the Aeolian Island is different. That's why Etna, I believe it's considered like a intraplate kind of magmatism, and it's a different kind of mechanism from the one on top. Unfortunately, I don't know too much to give about like the volcanic activity. I'm not a volcanologist, so I cannot give you like more details on the type of lava, the actual depth of the magmatic chambers, and the full insight of the mechanisms.
Yeah, just 2 days ago in my lecture of this workshop, I showed some example beneath Northeast Asia here. We have quite several intraplate volcanoes above the flat slab in the mantle transition zone. We think those intraplate volcanoes are caused by the upwelling flow in the big mantle wedge, from about 400, 500 kilometer depths. So those intraplate volcanism is quite different from the arc volcanism, which has a deeper origin of the magmas. Yeah.
Yes, and in here is the same. It's like a very similar, I suspect. And as I said before, the magmatism is different. The origin is different. I don't have all these details, but for sure it is like this.
But I'm happy to hear from you that there are also such a similar intraplate volcanoes above the flat slab in all this region. Yeah.
Okay,
thank you very much.
Cool.
Very nice.
Thank you.
Thank you.
Thank you, Prof.
Thank you, sir.
Sebastiano, I have one question. Sebastiano,
Yes, please go ahead.
Antonio speak. Yeah. So you have so person of smaller magnitude earthquake, they sudden too. So is it possible to invert negative magnitude earthquakes? It's a layman question only. Just I want to know. Am I audible?
Can you repeat the question because the internet is going on and off? Sorry.
Yes. Can you invert earthquake having negative magnitude?
Yes, there are quite, you mean like small and negative magnitude, right?
Yes, exactly.
Yes,
Yeah.
there are like a bunch of small earthquakes, both into the volcanic area, of course, with very small magnitude, and those are well detected by the dense network. But small events detected, even magnitude 1 or so, even in this tectonic regime. But sometimes the recordings are not that clear and that not that clean in order to perform the moment tensor. Okay, in principle, yes, you can. Then in real life, then things are more complicated. That's why the threshold is at least that we've reached now here in this region is 2.7 or so, 2.5.
Thank you.
Thank you, sir. Thank you to Professor Kyle, sir, and Professor Dapeng Zhao, sir, for your comments. So now, with your permission, can we take some questions from the participants?
With my permission, yes. I mean,
Yes,
you're
sir,
the
yes.
boss. Yes, you're the boss. So yes, fine. It's
Yes,
fine.
sir. Thank you, sir. So now I request.
You're muted, Chanmoy.
Sorry, sir. So now I request Dr. Antara Sharma to conduct the Q&A session. Over to Dr. Antara.
Thank you, sir. First of all, I would like to thank Professor D'Amico for delivering such an informative talk. Sir, there are lots of queries asked by the participants across the globe. So I'm going to read out the questions. So first question is, which one is more reliable velocity model, VM1, VM2, or VM3?
Now, actually, all of them are reliable for that area, and there are like some variations. Let me go back. There are some variations, as you can see, below the 40 kilometers, 35 kilometers, they go like you just finish to have the crust. The majority, the differences are within the crust. Velocity model 2 and 3, they don't differ too much, except the this portion over here, but also overall just the upper part is actually changing a bit. So those are taken from the fact that we selected several stations to create a set of stations all around. I don't have the image here, but a different set of station distributions, and then generating the extracting this from the 3D. But as you can see, the differences overall, if you want to simplify, are not too much. So we wanted to test, since there are like, even from the same authors, several models, we wanted to see what the effect it could be. Obviously, there are like a little bit of effects, when we look at the moment tensor and slightly at the depth, but within 1 or 2 kilometers, not more. So we are within the acceptable error, and they were used just as a test to actually see if our solutions are stable. Because the idea is that if we don't have something that is not known properly or well defined, same as the initial location that we use, are we still getting a reliable information on a large number of events that we can then depict the situation? And the answer, at least according to us, is yes, we can.
Thank you, sir. And the next question is, can we determine focal mechanism solution by using one station data? How much the result is accurate?
Now, there is a couple of nice paper. I believe it's, I don't remember if it's by Zhu and Tal. I don't remember if it's GRL or JGR, but you can look up. Okay, it's around between 2008 and 2012, something like that. And Zhu ZHU, in which they used actually two stations to actually get the moment tensor. And the techniques is promising. It's fine. Obviously, the more the better, in order to have a more reliable solution. Because sometimes two are enough, but then obviously, again, reality is a little bit more complicated than theory, right? So, but you can look up at these two papers, this couple of papers. Again, I apologize, I don't remember GRL or JGR, and you will find useful hints there.
Thank you, sir. And the next question is, you have been monitoring Mount Etna very closely. After the sequence of activities during 2018 to 2019, do you expect any eruption in the near future?
Well, the near future is the last month, let's say, and the last or during this summer, Etna has been very, very active. And colleagues in Italy at INGV have been very, very busy, and basically it's erupting every 2 days now, so it's quite active. But obviously, this is not due. That sequence that we were discussing later on is not the cause of this eruption now, but is the other way around. The set of the complicated and the mechanism, the volcanism mechanism, is giving rise to this particular, gave rise to that particular sequence. Okay, so far, at least during summer, it has been not energetic in terms of earthquakes generation as it was 2 years ago.
Thank you, sir. Sir, due to time constraints, we cannot proceed for more questions. So thank you again, sir.
Thank you. But I'm just an email away,
Yeah.
so just in case, feel free to send me an email or something.
Sure, sir. Thank you, sir.
Yeah.
Thank you,
Email is
Dr. Santara.
just enough.
So now we reach to the end of the session. So now may I request Ms. Anvesha Datta Hazarika to propose the vote of thanks, please. Over to Anvesha.
Thank you, sir. Namaskar and good morning from Assam, India. I deem it a great privilege to wholeheartedly thank the IVWGST 2021 family. I, to my best, would like to utilize this occasion on behalf of entire CSIR family to thank Dr. Sebastiano Di Amico from University of Malta for readily accepting our invitation to be a part of IVWGST 2021 family and for delivering such an insightful and informative lecture on the topic Seismotectonics of the Central Mediterranean Area. Thank you, sir, for sharing your valuable experiences and enlightening us with your knowledge. Besides, I also convey my sincere thanks to our Honorable Director, Dr. G. Narahari Shastri of CSIR NIST, Jorhat, for his surplus effort and keenness to make this event ensure. Thank you once again, sir. I feel fortunate to profoundly extend my gratitude to the international advisor of this workshop, Dr. Andrew J. Michael from USGS, USC, for his enormous support for this event. I extend my sincere thanks to our session advisor, Professor Daping Zhao from Tohoku University, Japan, for gracing us today with his honorable presence and for his constant guidance throughout this workshop. I also extend my sincere thanks to Session Chairperson Professor G.R. Kayal, former Deputy Director General of GSI, Government of India, and Co-Chairperson Dr. Saurabh Borua Sir, Chief Scientist of CSIR NIST, for always encouraging us and helping to smoothly maneuver the course of this workshop. It is my pleasure to thank Dr. Shantanu Borua Sir, convener of IVWGFT 2021, for his amiable commitment for this program. We once again thank you for your laudable initiative to unite the geosciences fraternity from around the world in a single platform via IVWGFT 2021. I bestow my earnest thanks to everyone involved in this session of IVWGFT 2021. We also earnestly look forward and encourage all to attend the next technical session for the day by Dr. Saurabh Borua from CSIR Northeast Institute of Science and Technology, India. He will deliver a talk on kinematics of Shillong Plateau and Eastern Himalayan region. With this, I conclude this session. Once again, I thank you all for being with us today. Have a wonderful day ahead. Thank you. Namaskar.
Thank you. Thank you, Professor.
Thank you.
Thanks to all. It was wonderful morning.
Yeah.
Thank you, Professor Sebastian. Thank you
Yeah.
so
Thank
much.
you.
Thank you,
Thank
Professor
you.
Zhao.
Thank you, sir.
Thank you. Nice
Thank you,
to see
Sebastian.
you.